Please title these notes Derivatives 14 Notes, Implicit Differentiation, and write today's date. At the end of this lesson, you should be able to use implicit differentiation to find the derivatives. Let's start off with some background. Until now, we've only taken the derivatives of functions. So remember, a function means for every x, there's only one y. So an example of that would be something like the equation y equals 3x squared plus 1. It kind of looks like that. And so if we want to take the derivative, find the slope of the tangent line, when x equals, let's say 1, there's only one point right here. And there's only one tangent line that we can draw. Implicit differentiation is used when we don't have functions. So for example, if we have the equation x squared plus y squared equals 16, that's the equation for a circle. And if we have where x equals 1, we have 2 points, right here and right here, where x equals 1, and they have very different tangent lines. One has a positive slope, one has a negative slope. And so what we're looking at here is we're saying that the slope of the tangent line is based not only on x, but also on y, because at a given value for x, there are two different y's. So let's write that. The derivative is based on both x and y. And y. We know to use implicit differentiation when we have an equation where y is not isolated. So let's give a couple of contrasting examples. So this is normal differentiation, and this is implicit differentiation. So our normal differentiation, let's find dy dx. So remember, this is another way of writing the derivative of y with respect to x. This is also y prime. Let's say we have this. Let's say y equals 3x squared plus 1. Well, we know that if we're taking the derivative of y, the name for that is just dy dx. We take the derivative over here, bring down the 2, that's 6x, derivative of 1 is 0, and there we go. That's what we've done in the past. On this side, we're going to find dy dx if, and instead of just y, we've got y squared. Let's say that equals x squared plus 25. What happens in implicit differentiation is if we don't have y isolated, we're going to imagine ourselves taking the derivative of both sides of the equation. And if we ever have a y, that's an automatic box function. So what we're going to do is we're going to do the derivative of y squared equals the derivative x squared plus 25. This y is just some function of x. It could be 10x squared, it could be whatever. It's just something that we don't know what it is, but we're going to have to take the derivative of it. Kind of similar to what we were doing in derivatives 11. So this is going to bring down the 2 of the box, and then times the derivative of what's inside, and so what's inside there is y. Over here we're going to do a derivative like normal, that's 2x, derivative of 25 is 0. And one of the things to really be aware of here is that dx, the derivative with respect to x of y, has its own special name. It's just dy dx. So when we're looking over here, what we have here is 2y times dy dx, and that equals 2x. Now, the new piece is that this dy dx is sort of its own variable. And it can be treated just like any other variable. We can solve for it. So if we want to find dy dx, that just means we want dy dx by itself. And if we look right here, we can get this by itself if we just divide by 2y on both sides. Dy dx, 2 divided by 2 is 1, x over y. What this is saying is it's saying that the derivative of the tangent line, the slope of the tangent line, or the derivative, is just based both on what x is and on what y is, because this isn't a function. For each x value, there may be multiple y values. Now, we can actually think of this as being the same thing as this if we want to. We start off with y equals 3x squared plus 1. We can think of what we're doing here as taking the derivative of both sides with respect to x. This y, well, the derivative of y with respect to x has its own name, dy dx. We get exactly what we started off with. So you can think of what we've normally done as being exactly what we're doing now. We're just sort of highlighting a different piece of it. That different piece of it is that if we ever have a y and we're taking the derivative with respect to x, so what we're looking at is that these variables don't match. This is an x, this is a y. We're going to have this little dy dx because of the chain rule. Notice over here the variables match, so we don't need to have that little box. It's only when the variables don't match that this is an automatic box function. So let's do some more examples. Let's find dy dx if, let's say, x squared times y to the third plus 2y to the third equals 5x squared plus 3. Now, we see that y is not isolated, so we're just going to take the derivative of both sides. Right here, we see two things multiplied together. So we're going to have to use our f prime g plus fg prime. So we've got the derivative with respect to x of x squared times y cubed plus x squared times the derivative with respect to x of y cubed. So that's coming from this piece right here. Notice these variables don't match, so that means that this is going to automatically be a box function when we get there. Now we're also going to take the derivative of 2y cubed. Again, these variables don't match. We've got an automatic box. Notice that these two use the product rule. This was just along for the ride, so I'm just taking the derivative of that separately. Over on this side, these variables match, so it makes life pretty easy. We just bring down that 2, that's 10x, derivative of 3 is 0. So for this next step over here, the derivative of x squared with respect to x, these match, so there's no box needed, that's just 2x. The y cubed is just along for the ride. Here we've got x squared along for the ride, and we've got the derivative of y cubed. This is an automatic box, so we bring down that 3, and then have to take the derivative of whatever's inside the box. Derivative of y with respect to x simply is dy dx. That's what we're solving for, so it makes sense that we don't know what it is. Over here, this 2 is along for the ride. This is a box function. This 3 comes down. The y was in the box. These variables don't match, so we have to do the derivative of what's in the box, which is dy dx. We don't know what that is. We're going to solve for it. So for this one, we have 2 dy dx's. We want there to only be 1. We want to just solve for whatever dy dx equals. So what we're going to do is we're going to try to get all our dy dx's on one side, and every term that doesn't have a dy dx on this side. So these two terms right here have dy dx's in them. This one does not. So I'm going to subtract 2xy cubed from both sides, giving me 3x squared y squared dy dx plus 6y squared dy dx equals 10x minus 2xy cubed. Now, here's the thing. I see this dy dx in both of these. That means that I can factor it out. Just like if we had like 2x squared plus 3x or whatever, we see it as an x in both of them, and so we can factor out that x. So I'm just going to factor out this dy dx, and left over is 3x squared y squared plus 6y squared. Now I'm down to having just one dy dx. Generally, if you have 2, this is how you get them down to 1, you just factor that out. And now I can get all of this by itself, because this is multiplied times this, by undoing this multiplication. I'm just going to divide both sides by the 3x squared y squared plus 6y squared. That cancels these out. And there we go. Fairly complicated derivative, but it's just saying that depending on what x is, depending on what y is, both of those are going to affect the slope of the tangent line. Let's keep doing examples. The only change here is the automatic box around the y, and then having to solve for dy dx at the end. So let's find dy dx if (3x squared plus y squared equals 100 xy. So we're going to take the derivative of both of these sides with respect to x. And one of the things that we notice here is that we have a squared, so we've got a box function right there. So when we do this, we're going to bring down the 2. That's 3 times 2, that's 6. X squared plus y squared times the derivative with respect to x of x squared plus y squared. Now over here we've got two different pieces. This y is some function of x, so we're going to have to use the product rule. Here's our f, here's our g, f prime g plus fg prime. So the derivative of 100x, now we're just going to multiply by y, it's along for the ride, plus 100x times the derivative with respect to x of y. Remember, that's got its own special name, it's just dy dx. So over here we've got 6x squared plus y squared. And then here we're going to take these two derivatives separately because they're just added together. So we've got the derivative with respect to x of x squared, so we bring down that 2, that's 2x. The derivative with respect to x of y squared, similar, we bring down that 2, we've got that y, but this y is an automatic box function, so we've got to take the derivative of y with respect to x as well. Here the derivative of 100x is just 100, that y is along for the ride. We've got 100x, derivative of y with respect to x simply is named dy dx. Okay, so we see we've got a dy dx over here. We're about to have a dy dx over here. But they're on different sides of the equation. So what we have to do is we have to gather all our dy dx's on one side, doesn't matter. And in order to do that, we see that right now this dy dx is inside this parentheses. So in order to get it out of those parentheses, we first have to distribute this piece that's multiplied by it, and then we'll be able to get our terms on the same side of the equation. So let's start off by distributing this whole thing. So 6 times 2x is 12x, x squared plus y squared. 6 times 2y is 12y, x squared plus y squared. And then this is dy dx. Notice the x squared plus y squared is also being distributed here, so 6 times 2 is 12y, dy dx, x squared plus y squared, right there. So 100y plus 100x dy dx. Now, let's just get all our dy dx's on one side of the equation. So I'm just going to subtract the 100x dy dx over here, and I'm going to subtract this to get it over there. So I've got 12y x squared plus y squared dy dx. And then I'm going to subtract this 100x dy dx, so all my dy dx's are on this side. And over here I've got 100y, and then I subtracted this minus 12x, x squared plus y squared. Remember from the previous problem, we can factor out this dy dx. 12y, x squared plus y squared, minus 100x. And now I can just divide both sides of the equation by this whole big thing, and that'll get me dy dx by itself. There we go. These cannot cancel out because there is this subtraction here. However, we notice that every single term is divisible by 4, so we can reduce it a little bit. 100 divided by 4 is 25y. 12 divided by 4 is 3x. 3y minus 25x. And there we go. Okay, one more problem and then we'll do check for understanding. Let's find dy dx if the cotangent of x plus y equals x. So we're going to do the derivative of both sides with respect to x. We know that because there's this x down here, and we see that y is not by itself. So cotangent box function, the derivative of cotangent is negative cosecant squared of what's in the box. And then we're going to have to take the derivative of x plus y. The derivative of x is just 1. So negative cosecant squared of x plus y. We're going to take the derivative of these separately because they're added. The derivative of x is just 1. The derivative of y with respect to x is dy dx. Now that equals 1. Now, we can either distribute this here, which works just fine, or we can see that we can get this more by itself if we divide both sides by this negative cosecant squared x plus y. Either way, we'll end up with something that's equivalent. It takes a little less writing if we just divide both sides by this. So let's do 1 plus dy dx equals 1 divided by negative cosecant squared x plus y. And now if we just subtract 1 from both sides, we've got dy dx by itself. Finally, let's do a check for understanding problem. We want to find dy dx if y equals xy minus x squared plus 3. Do notice there are y's on both sides of the equation, so we do have to use implicit differentiation. Go ahead and try that one on your own. Restart the video when you're ready. Pause the video now. Okay, we're going to start off by doing the derivative of both sides. So that just gives us a dy dx over here. Here, notice that right here these are multiplied together, so we're going to have to do the product rule, f prime g plus fg prime. So we'll do the derivative of x times y plus x times the derivative of y with respect to x. This one is just a normal one, so we can just do the derivative right now. Minus 2x. Derivative of 3 is 0. So dy dx equals the derivative of x with respect to x is 1. Derivative of y with respect to x is called dy dx minus 2x. Now we want this dy dx by itself on just one side of the equation. So I'm going to subtract this x dy dx over here. Y minus 2x. Again, I can factor this out. Remember there's an invisible 1 here, so when I factor this out, dy dx, we're going to have 1 minus x over here. That equals y minus 2x. And I can get that dy dx by itself by dividing both sides by 1 over x. So that's y minus 2x over 1 minus x. That concludes Derivatives 12 notes.